Well, thank you so much for joining me, Jay. Super excited to have this conversation and really excited about what you're building with the Sei Network. So excited to have you on the podcast.
Awesome. Thank you for having me on, Logan. Huge fan of the podcast and excited to do a deep dive into what we're building over at Sei.
Perfect. I would love to start the podcast. I always try to give a little bit more context on who you are and what got you into the crypto industry. So I'd love to start there. What brought you into crypto and how'd you get into the industry more broadly?
Yeah, absolutely. So about me, my name is Jay. I'm a co-founder for Sei Labs. And I personally got into crypto back in 2017. At that time, my roommate was going through Binance Launchpad. So we tinkered on a few different projects together. And then afterwards, I ended up joining Robinhood. So I spent almost 4 years at Robinhood. I saw the company 10x, and I was an engineering lead when the entire GameStop saga happened, I guess 2 years ago now. And it was definitely not handled very well. I'm sure you were following along, Logan. I'm sure a lot of people or a lot of listeners were following along as well. I think the biggest issue from Robinhood's side is we did not do a very good job communicating what was happening internally. And there was just a complete lack of transparency, right? And what that experience highlighted to me is how when you have these systems that have no transparency and things start to go wrong, they can become very messy very quickly. And we've seen this play out time and time again, most recently with 3AC and FTX over the past several months. And one thing that people don't really realize is just how powerless you feel when you're an insider that's working at one of these places. Because you put your reputation, you put your career on the line when you join a company like Robinhood. And it's just incredibly frustrating when management completely keeps you in the dark about what's happening internally, right? And it's even worse when you're leading people in the company and they're coming to you with questions and you don't really have any answers to be giving them. So after going through that experience myself, I became much more of a decentralization maxi. Anything that happens on chain is inherently trustless, and that would have avoided a lot of the issues that we saw both with Robinhood and also in, I guess, more malicious cases like 3AC and FTX. So that's why last year, I guess 2 years ago now, back in 2021, my co-founder and I, we started building a decentralized Robinhood. And that's what led us down this journey of building what is eventually now Sei.
Perfect. No, great background context. And yeah, I was following along with all the Robinhood stuff. And yeah, it was unfortunate kind of how it unfolded as it did. But I guess now it was kind of a little bit of a blessing in disguise because it led you to build Sei. I would love for you to describe Sei because I have been fascinated by what you're building and honestly shocked that it took a little bit as long as it did for someone to build it. And so I'm really excited that you and the team are taking the approach that you have. So could you explain Sei? And I think you gave a little bit more of the background context, but ultimately what you're trying to achieve with the Sei Network.
Absolutely, yeah. So we were trying to build a decentralized Robinhood end of 2021. And this led to us looking down every layer 1, every layer 2, and all the other infrastructure that we could use to build an exchange. And that's when we started observing what we call the exchange trilemma. So basically between decentralization, capital efficiency, and scalability, every single exchange that's out there right now is only able to get 2 of those 3 things. So if you look at Uniswap v2, it gets decentralization and scalability, but not capital efficiency. If you look at Binance, it gets capital efficiency and scalability, but not decentralization. And we didn't think that the solution was to keep iterating on exchange mechanisms, right? That's what people have been doing for the past several years, and that has not worked. Instead, we think that the solution is to do a complete rewrite of the underlying infrastructure. And this is how innovation typically works. If you're familiar with the idea of application infrastructure cycles, it's basically that initially there's some infrastructure that gets created. This leads to new types of applications, some of which find product market fit. And then these applications then need more specialized infrastructure to give them better performance, better scaling, just better user experience overall, right? So if you look at the database industry, for example, you had original databases like Oracle get created. This led to the explosion of Web 1 and Web 2 applications, many of which found product market fit. And now you have more specialized solutions like Databricks Warehouse, which is tailor-made for AI and ML use cases. Similarly, we think the exact same thing is going to be happening in crypto. So we started off with Ethereum, very general purpose. This led to a lot of different decentralized applications that were created, out of which now I'd argue exchanges and stablecoins have pretty clear product market fit. There's a lot of other types of applications that have more nebulous or not really any product market fit. And for exchanges and stablecoins, now we're going to start seeing more specialized infrastructure getting created to better enable, good user experiences around these. So that's exactly what we're building with Sei. Our mission is to build the best infrastructure for exchanges. And if we succeed, then the decentralized exchange experience will be identical to that of decentralized exchange trading experience.
Can you talk about kind of how you describe Sei being the first sector-specific blockchain? Because I personally, outside of like the more general-purpose blockchains such as Solana or Ethereum, have been fascinated by or looking for kind of these sector-specific blockchains. And the application, like single application or app chains, to me, made some sense, but the sector-specific blockchains made much more sense to me in the sense that you get to keep composability, you get to have multiple different applications, but still preserving the benefits, kind of having the benefits of the general purpose blockchain with the composability, but having the benefits of the app chain by being tailored to a specific sector. Can you talk about a little bit about around your thought process on creating the sector-specific blockchain?
Absolutely. Yeah, so I think this is one of the major things we've done with Sei that is different than most existing infrastructure out there right now. So if you look at the distribution of Layer-1s in the market today, on one hand, you have general purpose chains like Ethereum, Solana, basically a lot of the bigger chains that we know of today. On the other hand, you have application-specific ones. So this would be Osmosis or DYDX v4. And rather than going down either of these routes, we started building squarely in the middle. So not quite general purpose, not quite application specific, but rather sector specific. And this unlocks an entirely new design space that allows us to benefit from both sides of the spectrum. So the main benefit with general purpose chains is the social coordination that it enables, right? So beyond just having composability or atomic composability between the different contracts that are there on the chain, I think the bigger thing is that there are all these teams that are part of this ecosystem. And they're all part of the same family that are all pushing that ecosystem to be successful. And this is something you just don't get with an application-specific chain. With app chains, it's basically a bunch of different chains, and they're all like streaming into the abyss. And it's really hard for any of them to really get that community built. Whereas with like Solana, for example, they've done an exceptional job building that community because there's so many different people. They're all building in that same ecosystem. Now, with application-specific chains, the main benefit that you get is customizability. So you're able to build really, really specialized infrastructure for the exact type of application or exact type of use case that you have. So by definition, the infrastructure that you have with an application-specific chain will be better for your application than it would be if you were building that application on a general purpose chain. So rather than going down either of these two extremes, we took the approach where we're building a Layer-1 chain with very specialized infrastructure for exchanges to get built. But at the same time, we're not building any of the applications on top. We're just building the infrastructure. And we're encouraging a lot of different builders to come and start using Sei to help their exchanges scale. So through this approach, what we've noticed is we've been able to have a lot of teams that are interested in building because there's a sense of credible neutrality if you're building on Sei. Whereas if you build on an app chain that is trying to become more of a general purpose chain, there's no longer that credible neutrality because as a DEX that is trying to build on a DEX app chain, you are now competing against the core chain itself. Whereas with Sei, we're just building the infrastructure. So there's no sense of that competition. And on the other hand, we have much better infrastructure than a general purpose chain. So exchanges that are trying to scale can make use of Sei to have better user experience and better performance over there. So that's why we went down that route. And yeah, I mean, we've definitely noticed that there has been a lot of interest from teams to start building on Sei.
It definitely makes sense to me. To play like a little bit of devil's advocate, today in the space exists kind of Ethereum is the more dominant platform. And Ethereum proponents would say, why did you not choose a layer 2 to kind of inherit the security of Ethereum and still get the scalability and the benefits of ETH? And then maybe following that question, in the opposite direction is kind of, again, the more high throughput chains such as, say, Sui or Solana and trying to, but still having kind of the generalized performance there. Why not build on one of those architectures instead of completely like building the infrastructure from scratch?
Yeah, that's a very good question. So originally we were considering all of the different alternatives you just mentioned. Approach number one would be just building on top of some existing general purpose chain. Approach two would be by building a rollup on top of Ethereum. Approach three would actually be by building a chain and by using some kind of shared security. And then the fourth approach was the one we ended up taking, which is just building a fully sovereign chain. So in terms of the first question you asked, which is around rollups, the fundamental issue with building a rollup on Ethereum is that it just cannot scale right now. With the current way that rollups work, a rollup will have all this execution happen off-chain, and then they will have a bunch of call data and a state hash that they will then write to the core L1 chain. So even though there's not a lot of computation happening on the core L1 chain, there still is a lot of data that's being written. So in the case of Ethereum right now, it has a target block size of 15 million gas, and each byte of data that is written costs 16 gas to write to the base L1 chain. So we actually did the math. It came out to be around 6,000 transactions per second that the current Ethereum network can support. If you're going to be having all the block space be reserved for rollups that are doing very simple transactions, such as just sending Ether back and forth between different accounts.
And now, just to make sure for clarification, this is before proto-dank sharding and then full sharding.
Correct. So exactly. So that's with the current state of the Ethereum network. We're able to get around 6,000 TPS. Now, if you have proto-dank sharding, it actually comes out to be 6.7K TPS. And I think dank sharding would be the true time when that scalability concern would potentially be mitigated. With proto-dank sharding, what happens is in addition to the normal transactions that you can, or the normal data that you can write to the core L1 chain, you can also include up to 8 blobs of data. And we did the math for around how much data could actually be included over here. And that ends up being around, there's like the target of 8 blobs of data. And I think there's like 4096 field vectors of like 8 bytes that is there in each of these blobs. So that comes out to be around 6.7K TPS with proto-dank sharding. So it's not really until dank sharding is there that you will actually see better performance. And I candidly don't know if dank sharding will happen anytime soon. Just looking at how long it took for the merge to happen, I don't think that's really realistic in 2023 at least.
Yeah, it makes sense to me. I have found very few engineers actually kind of running these comparisons. And ultimately, this is kind of what led me down to explore different communities outside of the Ethereum community, because I also ran the math and I was like, it seems like we're going to need a lot more data at the base layer to start achieving the things that we want to achieve, even with layer 2s. Exactly. So I appreciate you spelling it out kind of in your words. And then touching upon I know you wanted to be able to tailor the hardware even more, but why were like the high performance systems, one, Solana, and then two, kind of these other systems coming online, coming from Meta or Facebook with like Sui Aptos, why did that not work for your use case either?
Yeah, so the biggest thing that we noticed is that just building on top of a general purpose chain, every single general purpose chain right now was running into congestion issues, and it wasn't able to have specialized infrastructure to support more kind of granular types of applications being built on top. So we can go into the native order matching engine that we have built into Sei pretty soon. But having things like front-running prevention being built into the chain itself, that's not something that can be supported if you're making use of a general purpose chain. So that's why we were not too enthusiastic about an approach like that. And that's why we started considering building our own infrastructure. And that's when we also considered making use of shared security. So this would be like an Avalanche subnet or a Polkadot substrate-based chain, or even in Cosmos consumer chain. And the reason that we didn't go down that route is because we wanted to have complete customizability over the validator set, over the consensus mechanisms, and over basically the time to finality that we are able to get if we build our own chain. So after doing all the consideration from our side, we decided that the best approach is to just build a fully sovereign chain. And then from that approach, we're able to have complete customizability over everything we want, and then build the best possible infrastructure for exchanges.
Perfect. So you ultimately decided to choose Cosmos and build the Cosmos kind of SDK and build a chain from scratch from there. Can you explain why you chose like the Cosmos ecosystem to ultimately build your own Layer-1 and some of the technology improvements that you decided to make with the SDK?
Yeah. So first question around why Cosmos. We were extremely enthusiastic about the Cosmos SDK because it is an extremely modular framework that allows you to get a chain up and running very quickly. And then you're able to customize the parts of it afterwards that will be better for your specific use cases. So in our case, we're able to launch a testnet by May of last year. And this was a fully functional testnet with the native order matching engine built into it, and also a COS and WASM smart contracts that people could use to deploy on top. And then afterwards, we're able to make a lot of the more granular consensus level changes around Twin Turbo consensus that gave us a lot of the better performance that we've seen so far. So that's why we were most enthusiastic about Cosmos, because we were able to make our own sovereign chain that is modular, and it was also connected via IBC to all of the other chains in the Cosmos ecosystem. So for any chain that is focused on trading in exchanges, having this IBC connectivity from day one and having a trustless bridge that you can make use of, that is extremely powerful. That's why we got started with Cosmos. At this point, we actually have been working with Zaki and Marco. So Marco is the product lead for the Cosmos SDK, to essentially push Cosmos and Tendermint to their absolute limits in terms of time to finality, in terms of throughput. And that's why we ended up actually forking the Cosmos SDK. And we also forked Tendermint Core. And now we're running our own custom versions of it. And in terms of the specific things that we've done with Sei, there's 3 core innovations that we have. The first one is Twin Turbo consensus. So we basically ran a bunch of performance testing to identify which parts of Cosmos and Tendermint are inefficient. We identified block propagation and block processing to be 2 of the things that are extremely inefficient. So we were able to optimize those, and this helped us decrease our time to finality. So in our DevNet, we're seeing around 600 millisecond time to finality. In our internal testnets, we're actually seeing 300 millisecond time to finality. And this is an order of magnitude faster than what you would see on most high performance chains. For example, in Solana, they might have like 400 or 600 millisecond slot times, but the actual time to finality will actually be closer to 3 seconds. And also, if you look at like Sui, for example, that's also based off the papers that have been written about Narwhal and Tusk, that's closer to 3 seconds. And then like Aptos, Near, those chains have around 1 second. Avalanche as well have around like 1.5 second time to finality. So that was the first thing that we did. So I can go into the optimistic block processing and intelligent block propagation piece as well, if you think that would be helpful for the audience.
Yeah, I think that would be great. There's not very many chains in my point of view that have really focused on block propagation. So I'd love to learn what you have done to speed that up.
Mm-hmm. Absolutely. So around block propagation, what we noticed is that, so the way that block would get propagated is that I submit a transaction to a full node. That full node will include the transaction in its mempool, and then it'll gossip that transaction to a bunch of other nodes in the network. And then those nodes will all have the transaction in their mempool as well. Then one of these nodes will be the block producer. So they will look at their own mempool, they'll construct a block, and then they'll send that entire block over the network that is just composed of, let's say, 5 distinct transactions. And they'll send that over the network to every other validator in the network for those validators to vote on the block. Now, the problem here is that most of the time, and we actually noticed 99.99% of the time, these validators actually had all of these transactions that are there in their mempool. So what was happening is the validators would just be waiting to receive data that they already had in their mempool. So that was the key insight that we had. And the solution that we came up with over there is that instead of sending the entire block, what we started doing at a high level is in the block proposal message, we started to include transaction hashes. So transaction hashes for transactions A through E. And then we would just send one message over the network to all of the other validators that are going to be voting on that block. Then these validators would be able to reconstruct the block by just looking at the transaction hashes, because inside of the mempool, there's basically a map from transaction hash to the full transaction. So they're able to locally construct that rather than needing to wait to receive the entire block over the network. So in the happy path, they just wait for the block proposal message, and then they're able to construct the block locally. And in the unhappy path, where they might not have all of these transactions, then we just fall back to using the default way that Tendermint works, where the block producer would still send the entire block. They would have to break it up into multiple chunks, send that over the network, and then the validator could just wait to receive all of those over the network. So we saw pretty significant improvements in performance through this. The other thing that we did was optimistic block processing, which is also one of the core things that we've done with Twin Turbo Consensus. The insight that we had over there is that the way that Tendermint works is there will be someone who proposes a block, then validators will receive it, there will be a pre-vote message that gets sent, then there will be a pre-commit message that gets sent. So there's 2 rounds of voting that happen with Tendermint. And then afterwards, validators will actually start executing the block. So they receive the block, and then they just don't do anything for pre-vote and pre-commit. And most of the time, the block that is basically proposed is the block that ends up getting approved by the network, right? Generally, there's not any Byzantine validators or validators that are proposing invalid blocks. So what we started doing is validators, as soon as they receive the block, they will spin up a concurrent process, and they will start processing the block and updating a candidate state in parallel to actually having the voting happen. So then there's 2 outcomes from this. The first outcome is that the block will get approved by the network. And if it's approved by the network, then that candidate state will be the state that gets committed. So you end up having a decreased time to finality because block processing is happening while the votes are actually taking place. And the unhappy path over here would be if that block is rejected by the network. So in that case, it's pretty simple. The candidate state will just get discarded. And then for all future votes that happen during that block height, you will not be doing any of this optimistic processing to avoid having basically validators getting DDoSed and trying to do too much computation all at once. So we also observed pretty significant improvements from that. And that led us to the lower bound of 300 milliseconds time to finality in our internal testnet.
Interesting. And today on the testnet, transactions are approximately 600 milliseconds in finality. Is it the combination of both, or is one giving like much higher, I would say, performance increase than the other with the block propagation versus block processing?
Yeah, I mean, it depends on how much throughput is being handled as well. So in low throughput scenarios, it would be intelligent block propagation that is giving the decreased time to finality. Mm-hmm. And if there's a lot of computation that is happening that would actually result in the post pre-commit step taking a lot of time, where you're actually processing the block, and in that case, it'll result in optimistic block processing would result in improved time to finality.
Interesting. No, it's very clever. I'm always fascinated by the different systems and kind of the design choices that the teams make. There's a lot of like small nuances, but they matter a lot. So it's cool to hear you speak to it directly. So with that kind of block processing and intelligent block propagation, you're allowed, or you're able to have very fast finality. Why? Initially, you're comparing it to other blockchains. Why do you have such a fast finality when compared to others, and why is that important?
Yeah, so generally there's 2 types of finality. There are 2 types of consensus mechanisms that will result in either probabilistic finality or instant finality. So probabilistic finality means that you will have a block that is added to the chain, but that's not final. And there will be other blocks that get added either to that fork in the chain or to a different fork in the chain. And then only after a certain number of blocks have been built on top of that block will that be considered the canonical chain, and that transaction will be considered, or that block will be considered finalized. Now, the other approach is instant finality, which is what Sei has and what all Tendermint-based chains have. And the way that that works is that in order for a new block to be added to the chain, there needs to be 2/3 consensus between all the validators that are there in the network. So you need everyone to agree, and then that block gets added. And that way there ends up not really being any forks or any reorgs that can happen on any chain that has instant finality. So how does this actually impact the user experience? Well, the biggest thing is with probabilistic finality, you can't really be sure about whether your transaction is part of the canonical chain until a certain number of blocks has passed, right? So if you're a market maker and you're placing 2 trades, trade A will be included in block A, which is to purchase an asset, and trade B, which is part of block B, which is to sell the asset. But probabilistic finality, what could happen is that transaction A might go through. It might be included in the fork that ends up becoming the canonical chain, and then transaction B might be included in another fork, and then that fork just gets orphaned. So the scenario you could end up with is your buy goes through, but then your sell does not. And then you just lose a bunch of money from that, right? And this is actually what market makers that we've talked to observed on Solana and other chains that have probabilistic finality, which is why they ended up responding to this by using more conservative trading. So they basically ended up having wider spreads to account for the greater risk of this probabilistic finality. And this led to overall a worse user experience. Now, if you contrast this to instant finality or any kind of single slot finality, if you are able to be guaranteed that transaction A is included in block A, that's part of the canonical chain. Transaction B is part of block B, that's part of the canonical chain. Then you're basically guaranteed that anything that is confirmed is going to be part of that canonical chain. So you can offer tighter spreads, and it just leads to a much less risky trading experience overall. So that's why market makers are optimistic about instant finality. And it also just ends up resulting in a better user experience from that as well, because you have tighter spreads.
Yeah, it is fascinating. It's super interesting. One of the other things that you have also made improvements on the tech perspective is on the virtual machine and parallelization. I think today it's semi-comical to me that some chains are still kind of pursuing the single-threaded approach, where it seems fairly obvious that parallelization and the multi-core approach is going to be the correct one long-term, just being able to take advantage of modern hardware. Could you talk about what parallelization that you have done in the Sei network and what results you get from that in the actual network?
Yeah, absolutely. So Sei is currently the only Cosmos SDK-based chain to be making use of any form of parallelization.
And why do you think that is? Because I'm always confused by this.
Yeah, I think it's a combination of different things. The first thing is ABCI++ unlocks parallelization at the deliver TX level, which previously, that is something that we're actually running like a custom fork of ABCI++ as well. So that's just something that hasn't been launched yet by Cosmos and Tendermint. The second reason is for a lot of app chains right now, the problem isn't throughput. The problem is just getting activity happening in the first place. So you only really need parallelization once you have high throughput. So that's why it's kind of a premature optimization in the case of most Cosmos SDK-based chains. In our chain, our objective was to build a chain that is scalable from the get-go. That was a selling point for the exchanges building on top, which is why we chose to focus on that from the beginning.
That makes sense.
Yeah.
Sorry to interrupt you.
Yeah, we can talk about ABCI++ probably later during this conversation as well. But the way that we've approached parallelization is there's two levels of parallelization that we have done. The first is during normal block processing. So that's when every single transaction is being processed. And this could be stuff related to staking or sending and receiving Sei tokens or a normal COSM-WASM smart contract call. So this could be around an AMM or something that is not making use of Sei's native order matching engine. So that's the deliver TX parallelization. And then there's also end block parallelization. So at the end of the block, we have our native order matching engine that is running. And that'll be taking all the transactions and all the orders related to any of the order books. And they'll be executing them all using frequent batch auctions at the end of the block. So we can talk about that in a little bit. But for the deliver TX parallelization, the way that it works is at the chain level, there's the mapping between a message type and a template of the resources that it would be using. So for example, for a normal bank send message, there'll be a message mapping to a template, and this template will take in the inputs of my account address and your account address. And then at runtime, when the chain sees that this is the transaction that is coming in, or this is the message that is coming in, it'll be able to identify that my bank account and your bank account are the resources that are being touched. Now, once these resources are identified, then you can just construct a directed acyclic graph of whatever the dependencies are. So for any transactions that are touching my account, they will all need to be run sequentially to avoid there being any conflicts from happening where multiple transactions are touching state at the same time. But if there's transactions that are doing something completely different, there's a transaction for my bank account, and then there's a transaction that is updating an AMM that I'm not touching at all, then these can be run in parallel. So that's the high level approach that we're doing. At runtime, we identify what these resources are that are being used, and then we construct a DAG that is then used to parallelize these transactions.
Gotcha. So developers, just to re-articulate, do not have to specify which parts of the state that they're touching up front. The runtime will be able to do that for you.
Yes. So what developers need to do is they need to say that at the chain level, like they're going to need to say that this smart contract is making use of these message types. So that is the additional overhead for developers. And that's the one-time thing.
So I was wrong. Developers do have to state which contracts are stating up front.
Yes. So developers will need to define that when this contract is deployed.
Okay.
And they can update that afterwards as necessary. But for each individual transaction, the runtime will be able to identify that, okay, these are the resources that are being used based off those mappings the developer set up front.
Okay, that makes sense. So it's similar to the Solana and Sui model where developers state up contracts up front, and then if they're not overlapping with any other pieces of state, those can be run in parallel. And if they are contentious for a single smart contract, those are run sequentially.
Correct. And I think it's a little bit different than that because when the smart contracts are deployed for say, that's when you have to define the dependencies. But then afterwards at runtime, you can automatically figure out which resources are being used. Whereas in the case of Solana and Sui, you need to pass along whatever the resources are as part of the transaction. So that can lead to risk conditions that lead to things like crank turning, for example, because you don't know which accounts are going to be updated when you're submitting a transaction because you don't know what other transactions are coming in at the same time. And the runtime also doesn't know how to figure out which transactions or which accounts are going to be the ones that are being updated. So that leads to a little bit more a complicated experience with Solana and Sui. And yeah, so this is like the approach where like you have to define things up front. And then there's also the other approach that Aptos is taking with Lock SDN, where they have this optimistic parallelization. I'm personally not really a fan of that approach. And at a high level, the way that works is you'll try to run everything in parallel. And then for anything that ends up having a conflict where you're touching the same state, you'll then have to rerun that sequentially. And in theory, this sounds really good because you can have things just optimistically getting processed very quickly. But in practice, what ends up happening is there end up being hotspots where you're going to have a lot of the transaction activity happening anyway. Like if you look at Ethereum L1, it would be stuff like Uniswap and OpenSea, where most of the transactions are touching the same state. So in that case, what you would do is you would just run everything in parallel, and then you would just rerun everything again sequentially. So that just adds additional time to processing. So I mean, that just results in greater time to finality from the user experience standpoint.
Yeah. Then, I mean, earlier we were talking about time to finality, and you were mentioning Solana and Sui slightly longer finality times than Aptos. So why, I mean, with optimistic block propagation or runtime, why, as of today, is there confirmations, in your words, faster than the other two?
So I think the biggest difference between Sei and Solana is instant finality versus probabilistic finality.
With Aptos specifically, because they're doing they're
using Aptos BFT, which is kind of similar to Tendermint. At least the literature that I saw online was 1 second time to finality from Aptos' side. I think that is a combination of the number of validators that they have and also the lack of the optimizations that we've made around optimistic block processing and the intelligent block propagation.
I see. Okay, interesting. And then one other additional benefit of having a parallelized virtual machine is the capability to do localized fees. Is that something that Sei Network is going to pursue, or are you going to have global fee markets initially?
So from the start of the network, we will be having global fee markets. And I mean, that's pretty easy for us to support because we have a mempool that can then be used to create these global fee markets, which I think Solana had a different approach around that. In the future, we will likely investigate localized fee markets, but I mean, right now, that's not the top priority. And there's also going to be other ways that we can help prevent congestion. For example, through having like stopping spam related to MEV transactions by having some kind of MEV redistribution structure. So realistically, that is something our team will explore in the future, but that's not something that is on the roadmap right now.
Makes sense. And then one other thing was kind of being more DeFi specific and the DeFi parallelization. Can you touch talk about that and kind of the real world results that you've received or see in kind of like number of order of operations?
Yeah. So we have market-based parallelization that happens at the end of the block. So the way that the Cosmos SDK works is that during the block processing stage, there's begin block, then there's deliver TX, and then there's end block. So you can define customized logic for each of these steps. In Sei's case, we're not doing anything super special for begin block. Deliver TX stage is where we've added in all of the parallelization that I just talked about. And then the last part of it is end block. So what we're doing with end block is we take every single order that makes use of the native order matching engine, and then we process them all together in aggregate at the end block. So we identify each market that each order is tied to. So for example, a Bitcoin spot market or a Sei perf market. And then from there, we aggregate all those orders, and then we'll execute all of them at the same uniform clearing price. And for each of these markets, we can run them in parallel because they're not touching the same state. So what ends up happening is we're able to construct, again, a DAG, a directed acyclic graph of the different markets that are being run. And then we can just have different markets be run in parallel if they're not touching the same state.
So it's parallelization based off specific assets.
Exactly. Parallelization based off specific markets that are being traded. And the result of what we've observed from this is 22,000 orders per second that they are able to process. So in this case, 22,000 orders, like each transaction can be composed of multiple orders through order bundling. And because of this, we're able to get 22,000 orders per second in the internal testnet, which is the magnitude more than you would be able to see on most high performance ecosystems, which tend to get around 1,000 to 5,000 orders that they can process every second.
Interesting. And so is that an aggregate 22,000 across the entire chain?
Yes. So that would be across different markets. I think those tests were done with 20 separate markets that were being parallelized. So yeah.
Interesting. And on the batching front, how many transactions are you batching in each?
For those specific tests, I think it was around somewhere between 100 to 1,000 transactions or orders per transaction that were being batched. We're still figuring out, like on mainnet, what the max number of orders that can be batched into each transaction is. But I mean, perhaps I should maybe give the listeners a more high-level overview for the third innovation that we have, which is the native order matching engine.
Yeah.
So the native order matching engine is something that is built into the chain itself, and it supports the two things that we've been talking about right now, which is the order batching and the end block processing. So specifically, the way that it works is if you're an exchange and you want to build an order book-based exchange, then you can just make use of the native order matching engine to create new markets very easily. And then this will also help with placing trades, matching trades, and filling trades. So all of this will just happen at the chain level. So the order batching piece that we're talking about right now is that because the chain itself has this kind of order matching engine primitive built in, as a market maker, you can actually submit multiple orders per transaction. So on other chains, you might need to submit one transaction per order. In Sei's case, you can submit, let's say, 100 orders per transaction and only pay the gas fees tied to that one transaction to make sure that that transaction is included in the block that you're trying to get those updates to happen. So that is what the order batching process is. The other thing that we do is because we're processing everything at the end of the block, we can actually prevent certain types of MEV, such as front running, related to these order book transactions by just aggregating everything at the end of the block and then making use of frequent batch auctions. So the way that frequent batch auctions work is that rather than sequentially processing every single transaction will get filled, or every single order will get filled at the same uniform clearing price. And through this, your order within the block no longer matters. So perhaps for a more concrete example around how frequent batch auctions stop front running, let's say that the order book has two transactions on it. One transaction for $10, the other order is for $11. And then two orders come in the block for people that want to buy the assets, right? Two market orders. So what will happen with sequential processing is that the first order will get filled at $10, and then the second order will get filled at $11. The way that it'll work with frequent batch auctions is that the first order and the second order will both get filled at the exact same price of $10.50, which is 10 plus 11 divided by 2. So through this approach, your ordering within a block no longer matters, and it helps prevent any of the front running that you would see happening in other ecosystems, where there's suddenly, in those ecosystems, there's incentive where if you see someone submitting an order, then you can place an order before theirs, have your order get filled, then afterwards place a sell order to sell that same asset at a slightly higher price to that user, and then profit off whatever slippage that user was accepting for that order.
So how does MEV ultimately work in the Sei network from that result then?
Yes. So I guess for the listeners, MEV, maximal extractable value, is the value that a validator or a block proposer can get by ordering transactions within a block. So one example of that would be the front running example that I just gave right now, where the validator, if they see that you submit an order, they can put in 2 orders before yours. One is to buy the asset. The second one is to sell the asset, to sell that asset to you at a higher price. And from their standpoint, it is completely riskless because all of that is going to get executed as part of one block. So there's no way that they were going to be left holding that asset without being able to sell it to you. So that would be one example of MEV. And that front running is just bad, right? That is extremely predatory towards users, and it's been outlawed in normal financial markets. So that's bad. But then there's also other types of MEV where there is an opportunity to make money, for example, through a liquidation or an ARB or an NFT mint, if you are the first person or one of the first people to be placing a transaction at the start of the block. So because of that, what you've seen in other ecosystems is a lot of spam, where people see that the value of the opportunity is, let's say, $1,000, and then the cost of submitting a transaction is substantially less than $1,000. They just submit as many transactions as they can to try to get that opportunity. So those would be the examples of MEV. And we think that the neutral MEV is something that we can redistribute to the chain and people that are stakers and validators to the chain. And front running is something that we're going to try to prevent whenever we have the ability to do so. So frequent batch auctions is what we're using to help prevent front running for anything related to the order matching engine. And for all of the other types of MEV, rather than having a scenario where everyone tries to spam the network to get that opportunity, we're going to be setting up something similar to flash bots on Ethereum, where there's an off-chain auction that'll happen. So there'll be some entity that is running these off-chain auctions. People that want to win this opportunity, this economic MEV opportunity, will submit bids to this off-chain node. And then this off-chain node will have some auction happen, and then they'll create a transaction bundle. And then they will then submit this bundle to the network to ensure that you get prioritized transactions in there. So if the value of the opportunity is $100, you might initially need to submit a bid for $1 because there's no one else that is competing for that opportunity. And then that bid will then get redistributed to the network of stakers and also validators. So that's how there'll be value pool happening for the chain. And then in the longer term, once a lot of these opportunities, there's more people that know about these, so they become more competitive. To win that $100 opportunity, you might need to submit a bid for $99.50. So then that entire value of that MEV opportunity essentially just gets redistributed to the chain itself. So that's what's going to be happening with MEV on Sei in the longer term.
Very interesting. No, it's some interesting design choices. I like it. Going back to like the parallelization per assets, is there something about the consensus algorithm that you and the team have uniquely enabled on the Sei network that is not possible on other high throughput networks? Or can the parallelization of specific assets also be done on other networks as well?
Well, you can't do it the same way as what is happening on Sei right now, because this is aggregating all the transactions together at the end of the block and then executing different markets in parallel. So you wouldn't be able to do that on any general purpose chain because they're not going to make a modification at the chain level to support anything related to just specific markets being processed at the end of the block. Because, I mean, they just are not built for creating the best infrastructure for exchanges. So that's why you wouldn't see something like that on Ethereum. But if you are building a custom chain like Sei is, that's why we're able to make those modifications at the end block level to support this custom logic.
Interesting. And one thing that you brought up a couple times is the ABCI. Could you explain what ABCI is and what is it?
Yeah. So if you're building with Cosmos and Tendermint, you'll be making use of ABCI, which I believe stands for Application Blockchain Something Computing Interface. And it's basically the interface between the application level and the consensus level. So I guess for a more maybe simple way to understand it, with Tendermint, you have different things that are happening. Initially, you'll have a transaction that gets submitted. Validator will run some logic, add it to its mempool. Then afterwards, a block proposer will create a transaction or create a block composed of different transactions, send that to the network. There'll be 2 rounds of voting that happen. And then people being the full nodes in this case, they would take the contents of that block, and then they would apply the state changes to update the state of the blockchain. So around there with ABCI, there's 2 touch points where you need application logic to run. The first would be when you're adding something to the mempool, you need to be running sanity checks to make sure that that transaction is not terribly invalid. So that's where the check TX logic is defined at the Cosmos SDK level. So that makes use of ABCI. And the second touch point would be when you're actually processing the block. That's when you need all of the state logic to be happening. So that's where with ABCI, you define the logic that you want with begin block, deliver TX, and block, and commit to define what the state changes should be. So that's one thing that we have been using. But then there's also ABCI++, which is an improvement of ABCI and allows for many more granular kinds of functionalities. So it allows you to add and customize logic when the block producer is preparing a proposal, when validators are processing that proposal, when you're doing vote processing as part of the pre-commit step. And with deliver TX, you normally only get 1 transaction at a time from Tendermint. But with ABCI++, you get this concept of a finalized block to receive all the transactions at the same time, and then you can process them however you want to. So in Sei's case, we actually ended up using ABCI++ by having our own custom fork of Cosmos and Tendermint. And we're using it for 3 different things. The first use case for us is around optimistic block processing. So this is during that process proposal step. Validators will spin up that concurrent process that'll be basically processing the block and then applying the state changes to a candidate state. So that's one of the use cases for ABCI++ for us. The second one is for parallelization. So with finalized block, you get all the transactions at the same time. And this allows you to construct that directed acyclic graph and then process them in parallel. Whereas for a normal Cosmos chain right now, you would be only getting one of them at a time. So you're not able to parallelize anything during that deliver TX stage. And the third use case for us is around oracles. So Sei has a native price oracle that is built into the chain itself. And this price oracle requires validators to be submitting transactions each block. And then one design approach that we were using before with ABCI is that all the transactions will get processed during one block, and then that price will be usable for the next block. But with ABCI++, what we're able to do is we're able to prioritize all of these Oracle-related transactions. So we process them initially, and then all future transactions in that block will be making use of the updated Oracle price feeds. So those are the 3 use cases we have for ABCI++. And yeah, I think we're one of the few chains right now that has been using it. And overall, it's been, I think, pretty significant for us to get this customized infrastructure that we're building.
Yeah, it's fascinating just how custom you can get with the stack. So with that customization and taking advantage of like a lot of the parallelization, what are some of like the node requirements? I'm assuming you need lots of cores. Can you talk about like, what you're looking on the node specs and then some throughput levels that you're expecting?
Yeah, so we don't have node requirements that are too different from other Cosmos chains, actually. So for example, the node specs that we have right now are, I think, identical to that of Osmosis. So the number of cores, I think, would be the main thing that we might tweak around in the future, depending on how much throughput the chain gets to. Like validators might want to use hardware that has a greater number of cores. But right now it's NVMe disk. It's going to be, I think, 32 gigabytes of RAM, 1 terabyte of the NVMe disk. And then in terms of bandwidth, it'll be around, I think what we used for our internal testing was 2 gigabits per second bandwidth. So it'll probably be something similar to that validators will be running on Mainnet as well.
Nice. And theoretically, if you scaled, say, the cores and gigabit, could you increase more throughput?
Absolutely, yeah. So I think the fundamental bottleneck for us with the 22,000 orders per second was the bandwidth. So if we were to increase the bandwidth, execution of the transactions across multiple cores like that is pretty easy to do, assuming that it is a parallelizable workload. So the biggest bottleneck was the bandwidth. And yeah, I mean, we'll have validators. We'll see like what validators are able to do in Mainnet. But yeah, realistically, more bandwidth would give better performance around that as well.
Yeah, I've been really trying as much as possible to do like unbiased like comparison of all these networks, and the bandwidth always seems to be the biggest bottleneck that each are kind of butting up against. With and the other thing on that, how does Sei Network kind of view decentralization being in the Cosmos ecosystem? There's kind of like an upper bound on like some of the node stuff. What are your thoughts on that?
So I think the biggest trade-off that we made with building Sei was making use of Tendermint, right? Mm-hmm. Tendermint gives you instant finality. It's already working right from the start, so you don't really need to spend years coming up with your own kind of consensus mechanism and then improving on that. The downside over there is that the number of validators that you can have ends up being capped at around 200. Like, I think Cosmos Hub has 175 validators, and that is the Cosmos chain that has the greatest number of validators. Most Cosmos chains have less than 100. And that is something that at the start, we're completely okay with that because we are decentralized enough. We have enough different validators to give the core things that we care about, which is trustlessness, transparency, and permissionlessness. So we get that even with anywhere between like 28 to 50 validators. But longer term, that is one thing that we're going to be thinking about, which is how do we increase the number of validators? Candidly, number of validators matters less probably than something like Nakamoto coefficient.
I agree.
Where if there's
Can you explain that though? I fully agree with this, but I don't think most people understand the differences or the nuances. So I would love to hear you explain it.
Yeah. So Nakamoto coefficient is the number of validators that would need to collude to basically result in at least liveness issues for the network. So in the case of a Tendermint-based chain, that would be how many validators are necessary to take over 1/3 of the network. And I mean, honestly, on most chains, like you might have like a bunch of different validators. Like on Ethereum's case, for example, you might have tens of thousands or hundreds of thousands, however many Ethereum has.
They actually only have like, I think it's a little bit hard to find these metrics, but I get stats from like between 6 and 10,000 full nodes.
Oh, okay.
On ETH. It's not that many compared to what they, and this is full nodes. It's not like the stakes. So, and that's an important distinction as well, but it's not as many as people would think.
Yeah. That's actually less than I would have imagined. But yeah, I mean, you might have this number that seems like a lot of validators, but if there's a small number of entities that actually control most of the voting power, then that results in these entities just being able to collude to take over the network, even if there are a lot of validators, right? So I think in Ethereum's case, the Nakamoto coefficient might be artificially inflated because there's a 32 ETH cap on every single validator. But logically, the number of entities that would be needed to take over the Ethereum network is not that many. I remember reading something that like Lido, Coinbase, Kraken, and I think Binance was the fourth one.
I think it's 2 right now, just Coinbase and Lido to get to 33%.
Okay. Yeah, to get to 33%, I think it's literally only those two. So I think the Nakamoto coefficient in voting power ends up being more important for decentralization than the actual number of validators. And I mean, I think this is one of the things that Solana has been doing really well, right? They both have a relatively high number of validators, and they also have a high distribution of the voting power between different entities in the network. So I think long term, that's what we would like to get to as well. But I think in the short term, we're going to be using Tendermint and encouraging people both explicitly and implicitly to try to basically delegate to different validators, probably by having at least some kind of like max cap per validator to force there to at least be a relatively relatively high Nakamoto coefficient. And then longer term, we'll probably be making changes to the consensus mechanism to allow for a greater number of validators.
That makes sense. And something that just came to mind. So how often are you creating new blocks in the Sei ecosystem? You have the super fast finality, but what are the block times looking like?
Block time will be the same as time to finality. So it'll be the lower bound that we observed was 300 milliseconds in our internal testnet. I think for mainnet, it'll realistically be higher than that because internal testnet was with all of the validators being from one geographic zone, whereas for mainnet, it'll be across multiple geographic zones. So I think somewhere between 300 and 600. 600 was in our DevNet, and in the DevNet, it was completely decentralized, and there were also validators not using the optimal hardware specs. So if you have better hardware specs and still decentralized, then I think it'll be probably closer to like 400 to 500 milliseconds.
And so you're able to choose the leader, which kind of ahead of time, which makes you able to have that fast block time.
Yeah. So we're making use of, I think it's a combination of the leader schedule being, you're able to figure that out beforehand. And also a relatively smaller validator set than a chain that, having instant finality with a chain that has a lot of validators is much harder to do. So using Tendermint makes it much more feasible to have that improved time to finality.
Interesting. No, it's, I personally really like all the trade-offs that you guys have made. I think it's an interesting design space to explore, and one that's definitely needed. One question that I asked on Twitter prior to this was some of your point of view around other ecosystems that are trying to do somewhat or similar things to the Sei Network, specifically DYDX, maybe Osmosis and Injective. Could you compare what you're doing to them?
Yeah, so I think the biggest difference just falls back to that example that I given before around sector-specific versus application-specific chains. So I think the biggest differentiator is going to be credible neutrality. For a project that is trying to build on Sei, you're not competing against the underlying chain. Whereas for an exchange that is trying to build on an app chain where the primary app is a DEX, you're going to be competing against both the primary app and also the infrastructure. So it's just kind of a losing proposition to be building on an ecosystem like that. Which is why at this point, Sei has over 100 teams that have committed to building on Sei. I think we've had over 40 or 45 teams that have also announced on Twitter. And I think one of the largest reasons for that is because teams are happy that they don't have to compete against the underlying infrastructure while still getting improved performance, improved user experience from the customized infrastructure. So that would be the first thing, and I think the primary thing. From more of a technological standpoint, I think the things that I mentioned before would also be differentiators against all the chains that you just mentioned. So Twin Turbo Consensus is unique to Sei. No one else is doing anything like that right now. So that is definitely going to be one of the things that differentiates performance. Parallelization would be one of the other ones. And then I guess for each of these chains, there ends up being something that's a little bit different. Like for DYDX, for example, they have off-chain order books. So every single validator has their own copy of the order book that is there in memory for them. And in some ways, this is better, but in other ways, this is worse. In terms of how it could be better, from a market maker standpoint, you can submit a order, and then that validator could confirm that they received that order faster than it would take for that order to get confirmed by the entire network if there needs to be consensus from that network. But on the other hand, one downside would be that there's more opportunities for MEV, because if a validator sees that you are submitting a transaction, then they could actually just include their own transaction beforehand, and then they can give you confirmation that they received theirs. But then the ordering would be their transaction would be able to make the profit, and then your transaction might end up failing, or it might get a worse price than the kind of MEV transaction would be getting. So I think that would be one of the trade-offs around that kind of an approach. But overall, I think all of these teams are doing fantastic jobs. And definitely it'll be pretty exciting to work with all of these to just grow out the Cosmos ecosystem moving forward.
And just to reiterate the kind of main things with the Twin Turbo, and like what makes it unique is the optimistic block processing and the intelligent block propagation.
Exactly. Yes.
Gotcha. Interesting. Cool. And then you mentioned also there's numerous teams kind of building on the Sei network. Could you talk about those? I think even some of them include different layer 2s exploring the ecosystem. Could you talk about one, just the general projects building on the layer 1s, I guess, and then talk about layer 2s and your thoughts of layer 2s using Sei?
Yeah. So first of all, Sei launched our testnet back in May of last year. And since then, we've been getting a lot of teams that have been interested in building on Sei. Initially, it was teams who were purely enthusiastic about the native order matching engine and being able to build a better exchange on Sei. Afterwards, when teams saw that there was a DEX community that was forming on Sei, we started seeing more and more kind of infrastructure-focused applications or just other types of applications that are not exchanges building on top. So at this point, there are over 100 teams that have committed to building on Sei. I think a couple of projects that I could talk about. So first of all would be Nitro, which is, I think, the project that you were alluding to with by talking about L2s on Sei. So Nitro is an optimistic rollup that is building on Sei, that is using Sei for settlement and for data availability. And the optimistic rollup itself, for its execution environment, is making use of C-level. So it's basically running a Solana, or I guess it's basically like Arbitrum, except it's running the C-level virtual machine, and then it's writing to Sei. So the reason that this was interesting to us is because as a team, we're talking to a lot of Solana projects that were interested in expanding to the Cosmos ecosystem. But the biggest reason that they were apprehensive about doing so is because they would need to rewrite their smart contracts. They would need to get them audited again. Ends up being a very time-consuming and expensive process. Whereas with Nitro, you can literally just copy and paste your smart contracts onto Nitro, and then it'll just work. So that was one of the things that we were very excited about, and the Nitro team has been able to deliver on that. So that's completely running on the Sei incentivized testnet right now. So you can play around with that. You can deploy Nitro smart contracts, and that is one of the projects I'm excited about. One of the other things that I'm excited about is Cargo. So Cargo is a predictions market middleware that is built on Sei, and Cargo is, I think the approach that they're taking is pretty unique, where they want different projects to be building on top of it for different geographic zones. So rather than them trying to build everything themselves, they're just building the middleware, and then other teams will be building prediction markets in India, for example, to support cricket prediction markets, like in Europe for maybe football prediction markets. So I think that's a very different approach than like people trying to build everything themselves. So I'm excited about that project. Fantastic team behind that as well. And the last one that I'll mention is Cargo. So they're building a lending protocol, and their longer term play is to make it more of a prime brokerage. So they're going to be using capital from this lending protocol to allow other smart contracts to borrow from that and to provide liquidity whenever they need it. So yeah, I mean, a lot of different types of applications getting built on Sei right now. And there's also a Sei incentivized testnet that is going on. So if anyone wants to play around with these applications, you can go to the Sei incentivized testnet, play around with them, and then there will be testnet missions for you as well that you can use to earn incentivized testnet rewards from performing certain activities in testnet.
And I guess the real question is, when mainnet?
Yeah. So we actually started our audits, in December, so a month ago. We're almost wrapped up with the audits right now. We're going to be launching an Atlantic 2 testnet pretty soon. And then afterwards, probably end of Q1, early Q2, there'll be the same mainnet happening. So happening pretty soon. There'll be the incentivized testnet rewards for anyone that participates right now. There will also be an airdrop happening. So there'll be a lot of ways for people to both get tokens to play around with the network and also just participate in the network right now.
Nice. The airdrop, I'm sure you piqued a lot of people's interest with that, but no, it's I'm personally fascinated by all the design choices. I am a big fan of ultimately having very high throughput, anything that takes advantage of parallelization. And I really like the approach of doing sector specific. I always thought like these app chains were ultimately going to do something similar, and I was surprised that it's taken so long to do so, but very happy that you and the Sei Network and the team are building this out, specifically focused around DeFi. It's an ambitious endeavor, but I'm glad someone's doing it.
Yeah, appreciate that. And I think last thought from my side is around our Atlantis program. So the easiest way to get involved and be part of the Sei community is to join the Atlantis program. And this is a fully community-led program. We have over 2,300 people that are part of the program right now, and they're creating a lot of the content that we're seeing right now. They actually created a Sei metaverse, I think around Christmas time. So you could literally go to this metaverse, and then there was like, I remember a Jay's lair or something. So they had different people from the Sei Labs team. They created like different environments from them. There was like a maze over there as well. There was like different pirate ships that people could visit. So super cool. So yeah, I mean, for anyone that's listening right now, wants to get more involved, you can follow us on Twitter. So SEINETWORK. And that has a link tree that'll show you all the different resources that you can use to learn more about Sei.
Perfect. Well, yeah, really appreciate the conversation, Jay. Appreciate you going into depth on a lot of the different technology choices that the Sei team has made and why they're actually important from the end user perspective. Fascinating to also hear kind of your history and what got you into crypto with being with the Robinhood team and ultimately the original goal of making an open source Robinhood. But yeah, appreciate your time, and I think people are really going to enjoy this episode. There's a lot of things for people to think about on this one.
Awesome. Yeah, this is a really fun conversation. Don't typically get to do this much of a technical deep dive. So appreciate the conversation right now, Logan. And yeah, thanks for listening in, everyone.
Perfect. Well, thanks again, Jay.